Let's say you are looking at some chemical reaction where reactant A becomes product B. You might ask the question, if I start out with some particular amount of grams of reactant A, how much product B should I end up with? Well, this kind of question is referred to as a mass-to-mass stoichiometry problem. Stoichiometry is that part of chemistry that allows you to calculate the relationship between different parts of a chemical reaction. To do this, we'll have to write out an equation where we'll start off with the amount of material A, and we want to end up with the amount of material B, in this case both in grams. Of course, somewhere in between, there's going to be some math involved. Before we get into this, you might wonder, why do we have to do this math in the first place? Can't the number of grams of A be equal to the number of grams of B? Well, probably not, for two reasons. One is that the material A could have a different number of atoms than material B, and it's also possible that material A could have different types of atoms than material B, and those different atoms actually have different masses as well. So for sure there's going to be some work involved here. So given that A and B can have different numbers and types of atoms, what is it that's going to bridge the gap from the mass of A to the mass of B? The answer? Moles. Consider moles the common currency of chemistry. Moles relates everything to everything else. In fact, in any given problem, if you don't know what to do first, it's probably to convert to moles. So, in our problem here, our first job is to convert a mass of A into moles, and then we'll go from moles back to the mass of B. Moles do a lot for you, so think of them as your friend. So now, let's solve our mass-to-mass stoichiometry problem. The first thing we're going to do is to convert the number of grams of A that we have into the number of moles of A that we have. Before we see the next step, we'll have to remember from the last video about the concept of molar ratios. Remember that in this example, we saw that for every 2 moles of aluminum that were used in the reaction, that 3 moles of copper were produced. And we were able to write the molar ratio in 2 different ways. Take some time with this slide or go back and see the previous video if you need to refresh your memory. So now that we've converted the number of grams of A into the number of moles of A, we're going to use the molar ratio that relates the number of moles of A to the number of moles of B to find out how many moles of B that we have. Lastly, we can convert the number of moles of B into number of grams of B. Thus, we've gone from the mass of A to the mass of B, and that's why we call it a mass-to-mass stoichiometry problem. Okay, let's try a real problem like the one from your lab. In this case, we'll say that we started with 0.500 grams of aluminum, but still in excess of the copper 2 chloride dihydrate. Now we'll bring back the framework from the other page, and now, as always, we start with what was given, which is the 0.500 grams of aluminum. Now, to convert from the number of grams of aluminum into the number of moles of aluminum, we'll multiply by the molar mass. Now, you'll notice I'm putting the number of grams of aluminum on the bottom. Do you remember why that is? That's because I want to cancel the grams of aluminum and leave moles of aluminum on top. Now this is where we connect the aluminum to the copper by using the molar ratio. Now let's recall again how the molar ratio could be written as 2 moles of aluminum per 3 moles of copper, or as 3 moles of copper per 2 moles of aluminum. Well, which one are we going to use? Consider that I'd like to get rid of the units of moles of aluminum and replace it with moles of copper. Therefore, I'm going to write it this way with moles of aluminum on the bottom. That way I'll be able to cancel the moles of aluminum and notice that moles of copper are left on top. And we've also represented the 3:2 ratio. Our final step is to convert the number of moles of copper that we have into the number of grams of copper. So again, we'll use the molar mass. In this case, we're going to put units of moles of copper on the bottom so they can cancel out, and then we'll put grams of copper on the top. Then we get the calculator out. Anything on the top is multiplied, anything on the bottom is divided. In this case, we get an answer of 1.76 grams of copper. At this point, you would compare this theoretical yield with your experimental value. Let's try a slightly different question. Again, assuming that we start with the same 0.500 grams of aluminum, let's say we wanted to just make sure that all of it reacts and not have any copper chloride dihydrate left over. So the question is, what would be the minimum number of grams of copper chloride dihydrate that we would need to use to just use up all of the aluminum so that the dihydrate is also used up? As always, we start with what's given, which is the 0.500 grams of aluminum. Next, as we use the framework from above, we'll convert this into moles of aluminum using the molar mass. Next, we're going to relate the number of moles of aluminum to the number of moles of copper chloride dihydrate. In order to do this, we'll want to make sure that we have moles of aluminum on the bottom. Now, the next thing is to remember how we saw in our chemical equation that there was a 2 to 3 relationship between the aluminum and the copper chloride. Now the question again is, which one are we going to use, the 2 to 3 or the 3 to 2 ratio? In this case, we're going to use this one because the moles of aluminum are on the bottom. So let's go ahead and fill out the rest of that ratio. 3 moles of copper chloride dihydrate per 2 moles of aluminum. So the moles of aluminum cancel out and the moles of copper chloride dihydrate are left. Now we have to convert moles of copper chloride dihydrate into grams of copper chloride dihydrate using the molar mass. Once again, the moles will cancel out, leaving us with grams. And little calculation, and we find 4.74 grams of copper chloride dihydrate were the minimum amount needed to fully react with the 0.5 gram of aluminum. Now let's look at this problem in a little more detail. Take our result. Now there are 3 possible things that can happen depending on how you set up the experiment. If we still start off with our 0.500 grams of aluminum and we combine that with the 4.74 grams of copper chloride dihydrate, we'll find, as we discussed before, that both reactants are going to be used up at the same time. When this happens, we say that we're combining the reactants in the stoichiometric ratio. This is often done when we want our reaction to proceed as efficiently as possible. Now, what happens if we end up using more than the 4.74 grams of copper chloride dihydrate? Well, in that case, we say that the copper chloride dihydrate is in excess. At the same time, the aluminum would be called the limiting reactant. That's because when the aluminum is used up, the reaction stops. In other words, the aluminum limits the reaction. At the same time, there's going to be some copper chloride dihydrate left over. The third possibility is that we start with less than 4.74 grams. In that case, we would say that the copper chloride dihydrate is the limiting reactant, and that means that the aluminum is considered to be in excess. In this case, the copper chloride dihydrate is going to be used up first. The reaction will stop, but there will still be some aluminum left over. Make sure you spend some time reviewing this slide. Now you have a chance to try these calculations using your own measured values from the lab. Many students find stoichiometry to be very difficult, but once you get the hang of it, you'll think it's pretty easy. But for now, good luck.